Welcome back to the Home Lab, and today I've got a really interesting demonstration and build to show you. What we're going to look at is a really retro form of computer memory. We're going to look at core rope memory. So if you know a little bit about this sort of thing, you might have noticed there's been a real resurgence in interest in sort of retro forms of computer memory, and particularly the types of memory that we used in the Apollo mission and the guidance computer that they used. And that computer used a very special form of memory called core rope memory. Curious Mark, if you've seen his truly amazing stuff on YouTube. He actually has some modules, and with his team he shows how they work and how they actually did their job in the moon landings. Anyway, what I thought we'd do today is have a look at how core rope memory works and try and explain the principles behind it and why it was used for the moon missions. And of course we need to build some electronics to demonstrate how it works. So counting away next to me here is my little core rope memory circuit that I built to try and demonstrate how it works. And the cores are here, and I'll explain what they are and what they're made out of in a minute. The memory's really interesting. This is sort of software that's actually hardware. In other words, the data that's in memory is not the cores themselves, but the data is actually these wires that either go through the centre of a core or go around it. And you can set this up so a wire going through a core can be indicative of a binary 1, and a wire missing a core can be indicative of a bit that's set to 0. So what I've done is I built a little circuit here that has some code stored in the ROM memory, okay, and I've got a little circuit here that makes the memory work, that displays the result of the memory, and also addresses each bit of memory so we can actually get the data out of it. So what we'll do now is we'll have a look at the principles of how core rope memory works. So the key to understanding how this memory works and where it got its name from is it's built using some little rings of ferrite. So that's iron powder that's sort of sintered together to make a little ring. And you can make these really quite large. So here's a large one. This is the size that I used for my demonstration. But in the real computers, we've got to get the scale right the way down, really small. So the little ferrite toroids or cores are so tiny, you can really only see them with a hand lens or a microscope. Now, just before we get into this in depth, I often call this rope core memory. It's actually called core rope memory, but the reason I call it rope core memory is it's a type of core memory that involves wires going through all these little ferrite rings, so when you lie it out on the table it can look like a rope. And I do that to not confuse it with magnetic core memory, which are these kind of core planes. And in fact, these don't have the memory density that core rope memory has. So what I'm saying is, if I say rope core memory, it's really my way of differentiating it from magnetic core memory. So let's get started and explain how this thing works. So I built a little core rope memory system here, and it's a lot simpler than the one that went to the moon, the Apollo guidance computer system. It does explain the sort of principle, but if you're into that sort of technology, you'll see that the one that was used for the Apollo guidance computer was rather more complicated. They had rather more wires going through these cores and all sorts of different currents. But we've got to start somewhere, so I've built a fairly simple one to demonstrate the working principles. So what did I want to do? Well, I wanted to write some code into the core rope memory that would light up a 7-segment display. So the code that I needed was binary ones and noughts that were going to tell me which segments of the 7-segment display to turn on. And if you know about these, but I'll explain it later, they light up by having different segments lit up. So I have to light up these 2 LEDs and these 2 LEDs to get the number 1, and I have to keep all the other LEDs off. So I've done them in pairs, as a normal 7-segment display would be. So we've got the top row, the high side on this side, the low side, across the bottom, this bit, and across. So that's 7 segments. And what I needed to do was I needed to write some code into the memory that would know which LEDs to light up to create which number. And then once I've got that code in the memory, I then need to address those places in memory with a circuit here, and what I've done is I've set it up to address in order, but it's actually addressing the data locations in reverse order, so it's counting down, which I thought would be quite a good sort of space sort of thing. So now let's have a closer look at how we store the data in this bit of the memory. So for a 7-segment display that's going to count down from 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, you've got 10 different states there. So that's 1 to 9 and the 0. And to display it, if you remember, the 7-segment display needs to light up correctly 7 different parts, depending on what number that we're showing. 8's my favourite because you just light up all of the 7 segments. So I can light up some of the segments, or for 8 I need to light up all of them, which is 7 of them. So I need a binary word that has 7 bits in it. So this computer uses a 7-bit word. So here's the first bit, the second bit, the third, the fourth. Later on in the build, I had this as the 5th, 6th and 7th, and I'd made a mistake. To make the wires go easily through these, it's the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th bit. So I had to take it all apart and fix this part, swap these two around. So if I want to light up on the 7-segment display the number 8, to do that I'm going to have to light up all 7 segments. So my binary word is going to be on. In other words, 7 ones in a string. Now think about that carefully. That's not what 1, 1, 1, 1, etc. is in binary. It's just I've coded this so each of these lights up 1 segment of the 7-segment display. Now we've got a 7-bit word, and we need to display 10 numbers, so that's all 9 including the naught. So we need 10 lines of code. Now, finally, I'm addressing those in reverse order, but I could use a circuit here that addresses them in any order I want. So the code is hardwired here into the cores, and then this part can address whatever line or address space that we want. So let's have a little bit of a closer look at how I've coded this. So to code core rote memory, you get one go at it, and if you make a mistake and it isn't noticed in the production stage, then that memory module becomes useless unless you can avoid using that one line of code. So the way it's coded is, if we pass a wire through the center of the core, that core will register a 1 or a binary on. If a wire comes outside of the core, and you might see the yellow wire here misses this first core, okay, that means that that will record a 0. So what you basically do is you lace wires in and out of the cores, and every word will consist of 1 wire that takes a route through some cores and not through others. So I think it's pretty clear that if we want a whole string of 1s, we send a wire right the way through the whole lot. If for some reason we want a string of 0s in our word, we have a wire that just bypasses all the cores. So you get the idea, and you could go through a core, not through a core, through a core, not through a core, so that'd be 1, 0, 1, 0, etc. So the code is hardwired into the cores. So what we need to look at now is, how does it transfer that data out onto the data bus, in the case to my 7-segment display here. So I'll just turn it on again. For some reason that I haven't worked out, the top 2 LEDs can be a bit dim at times, but they are actually working. So how does it actually do that? Because if you don't know about these things, you'll notice that if wires are going through cores and over cores, they're not electrically connected. So there's actually no electrical connection at all between the data that you've stored in the memory and the output phase. The connection is entirely magnetic. So, to explain how this works and how the cores work, you need to know a little bit about electromagnetism, and it's really useful if you know a little bit about transformers. You might want to watch my video on how transformers work. But to cut a long story short, transformers, and these cores behave like little transformers, have 2 coils on them. They have a primary coil and a secondary coil. So the primary coil is actually the single wires that either go through a core or completely miss it, in other words come outside it. And the secondary coil is the red wire that you can see wound, and that goes out onto the data bus. It shows the data that we actually want. So to get these to pass data from the single wire out onto the data bus, we need to magnetically connect between the 2. Now, if you know a little bit about transformers, if you put DC in a wire, it will not create a changing magnetic field in that wire. With no changing magnetic field, that won't be picked up by this secondary coil, so you won't generate an EMF in it, you won't generate a voltage, you can't drive any current. It doesn't work. Okay? So what I've got here is a circuit that creates a very high frequency AC signal. So if we pass AC through one of these wires, if it's going through the middle of a core, it will have a changing magnetic field. That changing magnetic field will induce a voltage in the secondary, that's the red wires. That voltage can drive a current and switch on some LEDs. So the long, tall and the short of it is that the cores act like little transformers, and if you think about it, they have to be AC, and secondly, if a wire misses a core, even if it's got AC going through it and therefore a changing magnetic field, that can't be picked up by the core's secondary winding, so that will record a 0. So in many ways, it's a whole series of transformers that have 1 turn on the primary, and in my case I think it's about 35 or so turns on the secondary. So if they pick up an AC pulse, they output data as a 1, and if they don't pick up an AC pulse, they output data as a 0. Okay, so now for a quick explanation of all the electronics we've got here, and it's not as difficult as you think, so don't worry. So clearly we've got 9-volt power supply. Then I've got a 555 timer here ticking away seconds, and the red LED shows it ticking away. That goes into a decade counter, and a decade counter is fairly simple. Every time you put a pulse on it, it switches off all the data pins on it, bar one of them. Then when it gets the next pulse, it moves to the next data pin and the next. So basically you get the first pin switching on, then the second, then the third, then the fourth. So it's a bit like counting up or counting down. As those pins become live, I feed them into a Darlington driver. I needed 2 of them because these didn't have enough pins on them. And a Darlington driver just creates a little bit more current. That then goes into a series of 10 transistors, and those transistors switch on every time they get a pulse from the Darlington drivers. So you'll get the first one switching on, then switching off, then the next one switching on, switching off. So it'll slowly count through the transistors from 0 to 9. So we've basically got a series of electronic switches here that are switching on in order, the first, the second, the third, the fourth, the fifth. Those can be used to switch on the first data line, the second data line, the third one. In other words, address the memory here. And I'm addressing it in sort of reverse order. The next thing is, how do we get the AC on these cores? Well, fed into the transistors is another little circuit here. It's the one with the blue LED. 555 timer again, and this one is operating at a very high frequency. I think it was about 60 plus kilohertz. And so that's producing an AC signal, and that AC signal is fed to all of the transistors, but will only pass through the one that's switched on by the decade counter. So we get AC signals in turn passing through each of these data lines up through the lines that pass through the cores. And so if the first data line is switched on, we've got AC going through all of this. Some cores will pick up the AC, some won't if the wires are on the outside, and that will light up the appropriate segments on the 7-segment display. So we've got slow counting that addresses each memory line, each memory space, and then we've got high frequency AC, which is used along those lines to create the signal that the secondary on each little core can pick up. And finally, I'm sure you know if you know about transformers, but you might say, well, why do you need the cores in the first place? Well, to create a really tight and really strong magnetic field, it's always a good idea to build your transformer coils or your little coils onto something that will become magnetic as well. So that will make the magnetic field stronger and more compact. So we need less wires and less turns. So that's why the little cores are here. But the crucial thing is they mustn't stay magnetic. As soon as the AC signal goes, or if the AC signal is going up and down, they must magnetize, demagnetize, magnetize, demagnetize. And that's one of the main differences between core rope memory and magnetic core memory. So well done on following that, and hope you've got a good understanding of how the circuit works. Now, if that's all too much, then just skip to the end of the video and I'll say goodbye and thank you for watching. But what I'm going to do now is I'm actually going to show you the circuit diagram very quickly that I invented, that I then built to make this circuit. And then what I'll do is I'll show you how I actually put it together, all the stages of trial and things working and not working to get the circuit finally working, and then you'll see the build process right up to the end stage when we actually got the whole thing built. So come and have a look at the circuit diagram, and then why not stay with me and see the build process. Okay, so let's now have a quick look at the circuit, and don't worry if you don't understand circuit diagrams that much. I'll break it down into simplified blocks. So this is the circuit that provides the high frequency AC that will cause the cores to actually pick up the data. So what we need is some power coming in, then we need a 555 timer that's set up with the right components to tick very rapidly, around 60 kilohertz. The output from that 555 timer goes to the blue LED, so you could see that was on. It's actually flashing, but so fast you can't see it. And then what it does is it is wired directly to all of the wires going through the cores. So that's 10 different wires going through the cores. But no current can pass through the core wires, the primary, unless the transistor is switched on. So each wire at the other end has a transistor. I've just drawn one here, but there'll be 10 transistors, and each of those transistors is switched on in time from a decade counter. It's another circuit that I haven't drawn here. And if the transistor is switched on, a current will flow through the primary and will register that line of code, so that specific word. As soon as the transistor switches off, no current will flow through that particular wire, so it doesn't read that line of code. So that's the high frequency end. Now let's look at how we address each area in memory. Okay, so now let's look at the circuit that addresses each memory space in time. So we've got the power supply, we've got another 555 timer set up with components to make it tick slowly, to tick every second. And I've got a variable resistor here that can vary how rapidly it ticks. Its output goes to a red LED here, and that's the one you could see that was going flash, flash, flash. Then into the decade counter, so that's the 4017 chip, and what that will do is it will switch on this pin, then that one, then that one, then that one in order, get all the way down to 9, so that's 10 different pins, and then go back again. That then feeds into our Darlington driver. I needed 2 of those because there aren't enough pins, so I've drawn one here and the second one there. And that just creates a little bit more current that can then turn on each individual transformer. So we've got 10 data lines coming out here, or address lines more correctly, and we'll have 10 transistors. I've only drawn 1. And if that transistor turns on, we'll have a current, AC current, coming from our AC circuit going through our specific wire that we're addressing, that's going through the 7 cores, and then that will be onto the core's secondary winding, and that secondary winding will pick up that changing AC in the primary and will switch on the bits of the 7-segment display that we want indicated. Then of course it goes to the next wire and the next one and the next one, so it goes to all 10 wires in turn, so it can light up the 10 numbers on the 7-segment display in order, and I've got it wired back to front, so it counts down, so it goes 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So with the circuit diagrams sorted, I started the build process, and I'm always modifying the actual circuit diagram as I build because I find things work and things don't work. So I always start off by breadboarding every little bit of the circuit. So the first thing to do was to build the decade counter bit. So I built that on breadboard and got it counting, and got it counting at a 1 second rate. So I was happy with that, and I was happy that the Darlington arrays worked, and I was happy that the transistors were beginning to switch. The next job then was to play with the high frequency side, and it took me ages and ages, firstly winding the little cores and working out if one wire was going to pass through, because we always use one wire on core rope memory, how many turns I needed on the secondary, and I think I got about, I think it was about 35 or something like that, and it was a pretty tedious process winding red wire around each one of these, and I knew I needed 7 of them because I needed a 7-bit word for each bit of the 7-segment display. So once I'd done that, it was a case of playing with the other 555 timer to get an AC signal that would definitely work and cause the cores to magnetize and demagnetize. So I played with a range of frequencies and finally came up with a frequency of around 60 kilohertz, maybe a little bit higher, and that seemed to work quite nicely, because what it meant was that if I put a 60 kilohertz signal on the data wire going through a core, the core would pick up that AC signal, and there was enough voltage generated, enough induced EMF to light the LEDs. And the interesting thing about the LEDs, of course, I know they're DC devices, but of course if we're feeding AC to them directly, they're just flashing very rapidly. They're going on, off. They're missing the negative part of the cycle. So after the secondary part of the transformer core winding, it's straight to the LEDs. There's no other electronics needed. There was enough voltage to light the LEDs. I got some really interesting waveforms as well. Now, those of you who are really good with these sort of circuits will go, crumbs, why didn't you design it this way or that way? I was just messing around of an evening, and I was just interested to see what would happen, and I think it's probably due to a bit of inductance or something, but the waveform we got on the oscilloscope was really interesting, and it was useful to have an oscilloscope to make sure that I could actually see there was an AC signal, that it was high frequency, and that it was pulsing on and off when the decade counter counted. So a lot of breadboarding, and then slowly but surely I transfer those to circuit boards, and these circuit boards I've used quite a lot. They have a sort of grid on one side and then some copper pads on the back that I can solder onto. Finally, when I built the sort of 2 circuits, I built a connecting board, and then I put the whole lot just onto a Perspex sheet, and actually I'm really quite pleased with the result. So now for the rather fun and somewhat tedious bit of actually putting the code into the rope core memory. So what I decided I wanted this one to do was to have code in it that makes it count down from 9, a bit of a sort of countdown or sort of launch indicator. So this 7-segment display I've built here, what I want it to do is to go 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, if you remember from my massive 7-segment display video, a 7-segment display is made up of 7 different sections which can be addressed independently. And normally you've got 1 LED for each section, but I've used 2 here. And typically the top row is called A, then B, then C, then D, then E, then F, then G. You can sort of see one I've drawn here. So the first thing I want this to indicate is 9. Now, for the number 9 to show on a 7-segment display, we need all the segments lit up apart from this one here. So that one there. So A, B, C, D, E is going to be off. So A is on, B, C, D, E is off, and F and G will be on. So I've just put some labels here on each of the cores, and if you can remember, each of the cores is wired to one of the segments as indicated on the labels. So from the truth table, what I'm going to have to do is I'm going to have to make sure that A comes on, B comes on, C comes on, D comes on, E doesn't come on, F and G do come on. So the way to do that is to take a wire and thread it through A, through B, through C, through D, not through E. So the wire's going to come over the top or out of the way, through F and through G. And then that will be hardwired in. So if ever you address that line, if ever you sort of get the computer to ask what piece of data is on that wire, it will always be 1, 1, 1, 1, 0, 1, 1. In other words, the wire will miss the E core and therefore will not indicate a voltage in the sort of winding of this, and therefore E will be off. So if you got the hang of that, you can see I've got a truth table here, and the truth table indicates what wiring I'm going to have to do for each number that I want coded in the rope core memory. So just to pick another couple of examples, if I want the number 1 to be hardwired in on a particular wire, which we could address at any time, I'm just choosing to address them in order, then we only need B and C on. So a wire would come through B, through C, and would miss out A, D, E, F and G, so would never light those LEDs. And all I've got to do now is put 10 wires into the system from these contacts I've made here, which are going to be addressed one at a time, and make sure that each wire does the right line of either going through a core and making that a 1 or a bit equal to 1, or missing the core and making it a 0. So now to wire the whole thing up. And to do that, normally you just use enamelled wire or just wire of any old colour, and it looks like a sort of bird's nest of wire everywhere. But I thought for fun, I would actually wire it with wires that were colour-coded with the number that we wanted. So if you know the sort of international resistor and capacitor colour coding system, 0 is black, 1 is brown, 2 is red, 3 is orange, etc, etc. So I'll use those wires to wire up each of the numbers so you can see which number they're actually trying to light up. But of course it's not the colour of wire that makes a difference, it's whether the wire goes through a core or around it, registering a 1 or a 0 on our rope core memory. Okay, so let's do the 0 first. I don't know why I've chosen 0 first, but it's probably because the black was there. So for 0, I've got to go through A, B, C, D, E, F, but not G. So we're not going to light up that middle one there to make a 0. So I'm not too worried about how neat this looks. Not such a bad one to do this. So through A, through B, through C, through D. Now, because it's an AC signal, obviously, because these are like little transformer coils, it doesn't matter actually too much how the wire goes through, whether it goes through from the left or from the right. So here I am wondering whether I've cut off a piece of wire that's long enough for this. I think it is. I'm trying to talk and do this at the same time. Gosh, is that possible? So what have we not got to go through? We've not got to go through G. So we'll go over the top of G, through E and through F, and then come back to the line that drives that port there from the little board here. So if I cut the wire off and put it in there, we've now coded 111110 into our rope core memory, and that, never mind what we do with the rest of the electronics, that remains coded. So that's why this memory retains the coding you've put into it, even if it's been switched off for years and years and years. And I actually wonder what's happened with the Apollo rope core memory that still will contain its wiring, so will still contain the code it had when it was first built. Okay, so there we go. That is 0 coded into our rope core memory. Now let's do all the other numbers. Okay, so there we go. That's 0, 1 and 2 wired up, and I just hope I've got them through the right course, but we'll find out fairly soon. It's really tempting. I really want to turn it on now and test it, and that's actually a good thing to do, to see that I haven't made any mistakes. But I think I'm going to leave it right until the end when I've wired all of them up, and then switch on, see how we've got on. And respect to the sort of girls and women who did this back in the day for the Apollo missions. It was nearly always women and sort of young women at that period of time. I suppose because they were considered to be very reliable and very, very deft with their fingers and hands, or it may just been a sort of bit of an unfair division of labour sort of thing. But they were obviously putting through hundreds and hundreds of wires, not just the 10 that I'm doing. And the other thing that was really important was that all the wires were wrapped up and fairly rigid and with a bit of flexibility to make sure that they'd be safe in a launch configuration with the whole thing being shaken and vibrated. But mine, I'm just going to leave them sort of open and looped round like this. I think there's no point in tying them all down neatly. There's one other thing that's worth saying, rope core memory. So I can see the core. I can see that we've permanently memorised bits in these cores, but where's the rope bit? Well, the rope bit's really clever, that if I extended these brown wires to the 7-segment display and put the 7-segment display on a completely different board, then we'd have wires going through the cores, and we'd have wires from each of the sort of secondary windings on the cores going off to the 7-segment display. So the whole thing would just be held together with wires. So in other words, it would look like a string of sort of beads, a string of pearls they often referred to. In other words, a rope with beads on it, with wires coming in, which is for the sort of primary side, and wires coming out, which is the secondary side. And then you could bend that and twist it and fit it into the shaped box that you wanted, and then normally they potted it in, so poured in a kind of resin to keep it all in place. So about an hour later, and we've done 0, 1, 2, 3, 4, 5 and 6, the blue. And I just wanted to show you at this stage, before it's completely wired up, one of the wonderful things about rope core memory is that you can actually visibly see the programming in it. Now, I know that's obvious if you've been following what I'm saying, but if you have a look at where we've got to now, the blue down here, which is 6, and the green there, which is 5, don't need to light up section B on the 7-segment display. So this one here. And on the truth table, you can see that for 5 and 6, we have a 0. So you can actually see the wire miss core B. So you can visibly see the fact that a 0, don't light up, is coded into this section. And the wires do thread through A, C and D, so you can see that you definitely need to light those up. So I think it's wonderful that you can actually visibly see the code. It's not buried somewhere in silicon. It's actually a physical thing wired into the rope core memory. Okay, so here's the one I've been looking forward to for a while. It's 8, and 8's dead easy to do because you have to light up all 7 segments of the 7-segment display to make an 8. So the wire just goes through all the cores. And whilst I've been doing this, I've noticed I've made a few mistakes, and I sort of managed to sort them out. But I wonder whether the women who made these things back in the day for the Apollo launches, whether they ever made any mistakes. I think their work was checked and double checked because obviously they couldn't afford any errors. So let's get 8 wired up, and then 1 more to go, and then we're ready to test it. Okay, so that's 8 done, the one that goes through every single core, so that was fairly easy to do. And I'm reminded, and I forgot to say, that of course you have to specify your cores correctly, because if you do more and more programming and have more and more lines, you might run out of space through the centre of each core. So I think I'm okay here. There's plenty of room. So that just remains for me to wire up 9, and then we've fully programmed our rope core memory. So I do hope you enjoyed that video on core rope memory and you understand a little bit more about how it works. If you do, you're some of the way to understanding how the memory worked in the Apollo guidance computer. Anyway, this was a fun build and I enjoyed doing it. It didn't take too long actually, a few nights, and I always build things in modules. I'm sure I'll be doing another thing a bit like this at some stage, and maybe, if you're interested, I should do a video on magnetic core memory sometime. Anyway, thanks for staying with me. I'll be making another video soon, and I look forward to seeing you then.
8, 7, 6, 5, 4, 3, 2,